Well, I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day again. I thank you for these students. And I just pray that you'd be with Audric on the road and help him to find this video later, for it to make sense, for us to remember to move the camera, all that good stuff. And I just pray that you'd help us to understand a little bit more about Hilbert Space today, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. So, where were we? We were in chapter 4, and we just looked at some examples of operators, right? Let's see here. So next up, we were talking about bilinear functions, functionals, and quadratic forms, and I'm going to try to be real brief here in this section. I probably won't be able to resist the urge to not prove something in here, but mostly speaking, I think the things which are proved in this section are pretty, they're pretty clear, like the proofs of them. So first of all, what's a bilinear functional? So his bilinear functional is not really a bilinear functional, it's a sesquilinear functional, as he fesses up to. So bilinear for this book only, pretty much. Maybe this is bilinear in this context. I don't know. Like, you know, sometimes these words get used in different contexts, different places, unfortunately. Like, for example, you know, norm for us is a mapping from a vector space, right, to the field, whereas a norm in number theory tends to be a mapping which is integer valued, and it's not from a vector space. Well, it may be, but it's the meaning of norm is different in number theory. Anyway, so here that satisfies, for one thing, we have the phi of ax1, alpha x1 plus beta x2, y2 is alpha phi of x1, y2 plus beta phi of x2, y2, and then you've got that conjugate linearity in the second slot. So you pull out the alpha bar, beta bar. All right. And this is for any scalars, alpha and beta, and for any vectors in E, all right? So let's see here. Let me talk about, I mean, the first thing is what you're really, I mean, the central motivation in this particular context for studying this is that the inner product is a sesquilinear form. Like, so, you know, number one, you know, phi of xy equal to the inner product of x and y. This is sesquilinear, right? And I think if you think about it, some of the things I've proved for inner products are automatically true for sesquilinear maps as well. Like, for example, additivity in the second slot, you know. Okay, let's see here. What else? Another one we could do is like phi of xy equal to ax y, or phi of xy equal to x by. Here, where a or b are mappings from, linear transformations from E to E. So, or linear operation, operators he calls them, but his operators are always linear operators, right? Another example he gives is if you're working on well, if you have F and G are elements of well, F and G are mappings from E to C, right? If they're linear functionals, then you could define phi of xy by F of x, G of y conjugate. This would also give us a bilinear form. And it's kind of obvious, like, because you have the additivity in the x from F being linear, and then you have the additivity in the y from G being linear, but then you're conjugating it, so pull out the conjugate. Yeah. So there's further definitions. So symmetric means that phi of xy is equal to phi of yx conjugate for all x and y in E. So symmetric will, in the context of a real, if you're working in the real context here, then that reduces to just phi of xy equal to phi of yx, right? You can also talk about it being positive. It's positive means that phi of xx is greater than or equal to 0 for all x in E. It's a positive bilinear form. And what do you think strictly positive would mean? Yeah, phi of xx greater than 0 for what? For x not equal to 0. Of course, phi of xx has to be 0 because of the bilinearity. And then he defines what's a bounded bilinear form. How's that gonna be defined? So he says if E is a normed space. So I guess if I was being more careful here, this was just for a complex E at the start of this lecture up to this point. E has just been a complex vector space. All right. So this is just a complex vector space. And although I think here we're saying E is a Hilbert space, right? Inner product. So the definition is for a complex vector space. Here we're using the inner product to build our examples, so surely we're in the context of a Hilbert space, right? I guess it doesn't have to be complete. We could just deal with the inner product space. True. Fair enough. Fair enough. I don't think completeness is really at play here necessarily. And here again, this doesn't have to be a Hilbert space, right? You could talk about linear functions, whether or not you've got a inner product, you know. So. But this bounded definition here, so it's said to be bounded phi from E cross E to C, where E is normed linear space, is bounded if the absolute value of phi of xy is less than or equal to some constant k times the norm of x times the norm of y. for some positive k, and of course for all x and y. In E. Moreover, the norm of such phi is defined by norm of phi equals to the supremum over the norm of x equals to the norm of y equals to 1 of the absolute value of phi of xy. Now I think the inner product is a symmetric, strictly positive, bounded linear functional. In the boundedness, we have k equals to 1. That's the Cauchy-Schwarz inequality. And so, in view of this, I would just make a remark. If we have, phi of x comma y equal inner product of x and y on Hilbert space, right? Then, like I said, it's a symmetric, positive, in fact, strictly positive bilinear functional. What I'm trying to figure out is, can we figure out can you just calculate the norm of the inner product? I'm curious. What would the norm of phi be? So we're talking about the supremum of phi of x comma, so let me just write it down. It's the supremum of x comma y, right? Norm of x, norm of y, 1. Of course, this is less than or equal to, well, certainly, let's see here. We know that the norm of xy, the inner product of xy is less than or equal to the norm of x, norm of y. So that's less than or equal to 1. Actually, that's not less than or equal to 1, is it? That's, in this context, it's equal to 1. So, certainly 1 is an upper bound. And I think it's fairly easy to see that that's the supremum, because if you tried to find a smaller bound, you could easily pick you could contradict that you're looking at these things, because of course, if you put x equals to y, this is just the norm of x squared, and so. But yeah, I think it's fairly obvious that the norm of phi should be equal to 1 here. I don't think I quite proved it, but I kind of gave you an indication of how you might think through that.
Would that hold more generally just in any inner product space, not just the Hilbert space?
Well, are you asking if it would still be true if the inner completeness? Yeah, I don't know if completeness has anything to do with this particularly. Do we still have the Cauchy-Schwarz inequality?
Yeah, I think that holds independent of.
That holds independent of completeness. Yeah, that's just a property for inner product, right?
Yes.
Yeah. Yeah. So, I think this would still be true in an inner product space. I think you're right. Yeah. Yeah. Not, of course, all of my favorite inner product spaces are Hilbert spaces anyways. So it's kind of like, yeah. Okay, next up. Definition. Quadratic form. So if you have phi from E cross E to C bilinear, all right, then the function big phi from E to C defined by phi of x equal to little phi of xx. This is called the quadratic form. Well, it's called the quadratic form associated with, oh, you got it? Okay. Quadratic form associated with phi. And he says a quadratic form, big phi on a norm space E, is called bounded if there exists a function. So he's going to just go ahead and get his definition of bounded done with. What does it mean to have a quadratic form that's bounded? How's that work? Well, he says it's bounded if you have phi of x less than or equal to a constant k times the norm of x squared for all x in E. And he says that the norm of a bounded quadratic form is defined by, I think you probably could guess what this is going to be. It's going to be the supremum, the norm of x equals to 1 of the absolute value of phi of x. He says, note that the bounded quadratic form phi on a norm space will have, okay, great. He says the bilinear functional and the associated quadratic form have some property similar to an inner product, and the square of the norm defined by the inner product respectively. Yep, cool. I'll buy that. So just to make this slightly less mysterious, let me just take a step down from the clouds here and give you a specific example of what's going on. And I'm going to make it real, just to be different. So if you let E equal to Rn, and let's say phi of x comma y equal to the dot product of x and y. In this case, the quadratic form associated with the dot product is exactly x dot x, which is of course x1 squared plus x2 squared plus xn squared. And so I think it's worthwhile to write that down just so we have a better sense of why we're calling it a quadratic form. It's because it's a homogeneous polynomial in the coordinates, in the sense that every term you're adding has degree 2. So, yeah. And then the next up, he talks about something called the polarization identity. Polarization identity. And I feel like this is part of the mathematics which is involved in showing that you can't write the one norm as being induced from an inner product. Like that story is tied to this story. And I don't know the details right offhand either, sadly. But anyway, here we go. So If you have a quadratic form associated with a bilinear functional, here's how they have to be related, according to this formula right here. For phi of xy equals to big phi of x plus y minus big phi of x minus y plus I times big phi of x plus iy minus I times big phi of x minus iy. And the proof of the polarization identity on page 153 is very clear. He just writes out like what is, he finds he writes a formula for phi of alpha x plus beta y, and then he just specializes it for different choices of alpha and beta being 1 or minus 1 or I or minus I. And it's just a straightforward calculation. He adds those 4 equations and everything cancels except for 4 copies of the bilinear form. So it's okay. You know, I mean, there it is. So corollary to this, the corollary to this is if you have phi 1 and phi 2 bilinear functionals on E, so phi 1 and phi 2 bilinear functionals on E, then if phi 1 of xx is equal to phi 2 of xx for all x in E, that implies that phi 1 is equal to phi 2. Similarly, I'll say likewise, if you have ax comma x equal to bx comma x for all x in E, that for all is important, by the way. If this is just true for a given x, it doesn't tell you much. Then that implies that the operator A is equal to the operator B. And the proof is essentially by the polarization identity. Let's see if we can think through it. It shouldn't take us long. So let's see here. This is what? This condition right here is literally phi 1 of x equal to phi 2 of x, right? Big phi. So it's saying the quadratic forms are equal, right? But the polarization identity says that the bilinear form can be calculated by this particular formula of its associated quadratic form. So to prove that phi 1 is equal to phi 2, you just, right. So phi 1 is equal to, well, 1/4 of big phi 1 of all this, right? Which is equal to 1/4 of big phi 2 of all this, which then is equal to phi 2. So you just run right through the polarization identity to get that one. And then the second part here, I think it's kind of the same. Well, Hmm. I mean, the beautiful thing about the argument that I just gave you is that it is not depending on coordinates at all, right? So I'm fighting my base instincts to go into coordinates to try to prove the second claim, because, you know, for all we know, this is an infinite dimensional space, right? So if I use coordinates in infinite dimensional space, that doesn't really quite make sense unless I'm dealing with like that nice case, right? The separable, you know, the one with the orthonormal system and such. And let me look at his proof here. Okay. He says the proof for operators is obtained by letting phi1 of xy equal to a of xy. So he's let phi1 of xy equal to inner product of ax with y, and let phi2 of xy equal to the inner product of bx with y, right? Then what? Then phi1 of xx is equal to yeah, exactly. So thank you. You were thinking about this, but I'm just writing it down, right? Then from the first case, it follows that that phi1 is equal to, well, wait a minute. So what's that tell me? So that tells me that, that tells me that phi1 of x comma y is equal to phi2 of x comma y, right? So I've got that, you know, I've got axy is equal to inner product of bxy. Then the question is, why is that suffice to prove the operators are equal? I think that goes back to our last lecture. Let's see here. No, I didn't see it. I mean, maybe it's back in chapter 3 then. Not sure. I mean, well, I'm trying to think of what I have to work with here, you know. I mean, certainly if I'm on a, you know, finite dimensional space, I can prove this with flare. If I'm on the, you know, infinite dimensional, but the you know, separable infinite dimensional Hilbert space, that'll do it too, because, you know, in either one of those cases, I can define the matrix by well, goodness, I don't know. I mean, I feel like I'm forgetting something, but let me say this. If there exists an orthonormal basis for E, all right, then of course, you know, if you're talking about, if you have AX, comma, you know, EI equal to BX, comma, EI, that means that, you know, you can write AX as equal to the sum I equals 1 to whatever. We just say the sum over I to be sort of generic of AX, EI, EI, but that's equal to the sum over I of BX, EI, EI, which is BX. So what I'm saying is that you can use the inner product to find components of those with respect to a basis. This is probably a less, oh, come on, look, let me be less. This is hideous what I've done, and unnecessarily specialized. We can be better than this. We can do better than this. You know, as the people I detest often say, do better. So, sorry, oh man, that aggravates me. So if I rewrite this, I can rewrite this as, you know, AX minus BX comma Y equals to 0. Which then gives me that A minus B times X comma Y equals to 0. And then what was the axiom? We go back to the definition of inner product. What is one of the goodies we got to work with there?
I think they're both individually 0, which I like.
I'm trying to remember.
Yeah.
It seems like forever ago. Back at the start of chapter 3, you may recall the. Oh man, we don't have that.
They are.
Where is that?
So I think that's going to help us. But
Rats.
yeah, page 98 when it says they're orthogonal. No,
Yeah, I'm looking for something more. I want to use this to imply it has to be 0.
Yeah, the inner product x equals. Oh, wait, no.
Inner product x equal to 0 implies x equal to 0. Well, I mean, this does say that. Okay, so this is, well, it's closer to what I want, but I mean, this says that the vector, you know, AX, that whatever A minus B times X is, it's perpendicular to Y for all Y in E. So that should imply that A minus BX is equal to 0. For all X, right? Which then implies A equals to B. So I guess the question then is, how general were our theorems on perpendicularity, right? And See, the thing I'm a little bit hesitant about is that at no point has ever been said that given any Hilbert space, there exists an orthonormal system.
Oh,
You know?
yeah.
I mean, in the finite dimensional context, we're spoiled. If you give me a finite dimensional basis, I can run Gram-Schmidt on it, and we'll get a, an orthonormal basis.
Yeah.
So I'm a little fuzzy on this here. I feel like this might be a chink in the armor of the book right here, unless I'm missing something.
Could the Gram-Schmidt be on page 110? It's acting like the Gram-Schmidt to be applied on,
110.
sequences of vectors.
Hmm.
So would that, if it's countably infinite,
Huh.
could we do that?
Given a sequence of linearly independent vectors, so you can do. So we can do Gram-Schmidt on a sequence. Okay.
But I guess if it's uncountable.
I guess this question is there a sequence which forms a basis for a given Hilbert space, right?
Yeah.
Because we've always, like, the more interesting theorems in section 3.4 assume the existence of an orthonormal sequence in the Hilbert space. And then, he assumes, definition 3.4.12, he assumes that that everything can be written in terms of that. He basically is, I don't think there is ever an existence for an arbitrary Hilbert space that's stated here. And a Hilbert space is called separable if it contains a complete orthonormal sequence. Finite dimensional Hilbert spaces. So I think he has. And then we have that every orthogonal set in a separable Hilbert space is countable theorem on page 120. And then theorem 4.27, if H is infinite dimensional, it's isomorphic to L2, but that assumes that H is separable.
Yeah.
So I'm assuming there are non-separable examples, but he doesn't want to talk about them.
Apparently,
Or he probably said something about them somewhere. I just don't have a photographic memory, right? Okay, let's go on. Let's,
Sorry about that.
no, you're fine. It's my fault. I'm the one who's been belaboring this. Let's go on here. So, all right. I'm going against my. This was not. No, it was not useful. What I just did. Let us go on here. All right. So let me just state the rest of the theorems here, and I will fight my instincts to prove things. So theorem 4.3.9, bilinear functional on E is symmetric. It's symmetric if and only if phi is real. The corresponding, and that you can almost see that immediately, right? Because you've got phi of xx, right?
Yeah.
Conjugate is the inner product. Well, it's not inner product, it's phi of xx, right? Which is, if it's symmetric, this, which is that. And so if something is, I have phi of xx, I'm a dummy, phi of x conjugate. So if it's equal to its conjugate, it's real. Okay, great. Then next theorem. Oh, you already moved me, didn't you? You're fast. I don't even see you do it. A bilinear functional phi on a norm space E is bounded if and only if the associated quadratic form phi is bounded. Moreover, I'm just going to write this part of it. The norm of the associated quadratic form is less than or equal to the bilinear form from which it is associated, which is less than or equal to twice the norm of the, so yay. And again, it's the polarization identity paired with like the triangle inequality when you look at the proof of these things. And then theorem 4.311, phi a bilinear functional on norm space E, let big phi be the associated quadratic form. If phi is symmetric and bounded, then their norms are equal. If phi symmetric and bounded, then the norm of the bilinear form is equal to the norm of the quadratic form associated. Theorem 4.3.12. If you have a bounded A is an operator on a Hilbert space, bounded, then the bilinear functional defined by the combination of the inner product and the operator like this, inner product ax comma y is bounded. And more than that, the norm of the operator is, equal to the norm of phi. All right, great. So, and I guess I'll slow my roll here for just a second and try to prove that. It doesn't look too bad. He says uses Schwarz's inequality on the this guy right here. So absolute value of the bilinear functional x and y as so defined is less than or equal to the norm of ax, norm of y, right? But we know that A is a bounded linear functional, right? So by definition, well, basically by the way the norm works for the operator, this is less than or equal to the norm of A, right? Times the norm of x. So for a bounded linear functional, that's one of the properties of the norm of the bounded linear functional is that you get that the norm of the linear functional times x is less than the norm of the bounded linear functional times x. It's not an equality there, but it's, like that. And then, let's see here, what else? You're fine, I'm just checking my Zoom. And the audio. It never hurts to check the audio every so often. I'll tell you that. Right, he says, on the other hand, if we look at the norm of ax squared, that's equal to the inner product of ax and ax, right? Which, of course, we can wrap that in absolute value bars, right? which is what? He says that's equal to phi of x comma ax, absolute value of phi of x comma ax, right? So you're putting y equal to ax there, which is less than or equal to the norm of phi, the norm of a, oh, I'm sorry, I got lost all of a sudden. Oh, so just using the thing right above. See, I have that the absolute value of, if I put x equal to ax and y equal to ax, that gives me this here. Which of course is equal to the norm of phi times the norm of ax squared. He says, therefore, for ax not equal to 0, we have norm of ax less than or equal to norm of phi times the norm of x. Oh, okay, right, well, that's just this inequality right here. He's just dividing by the norm of ax. You see that?
Oh yeah, norm of x instead of norm.
Yeah. Of course, if ax is not equal to 0, the norm of ax is not equal to 0. And he says, since the above inequality is trivially satisfied if ax is equal to 0, we obtain that the norm of a is less than or equal to the norm of phi. And what's that tell us? Oh yeah, we already showed the other way. Right. Right. Whew. So they're equal. Okay. I thought that was going to be more fun than it was. I need to start to acknowledge that unless I eat something before I have this lecture, I'm going to run into severe difficulty about this far into it. Like, I just run out of energy. All right, we still got some time. Cool. Let me go on here. So, theorem 13, I will erase some of these things. I think we don't need that. I think we're good on those up there. Probably don't need the bilinear anymore either, but I'm gonna leave it. Actually, what am I doing? I could get rid of that, couldn't I? Probably could have saved myself the trouble even writing that today, since we already know that. But, oh well. Poor planning on my part. So here's theorem 4.3.13. It says that if you've got phi bounded bilinear functional on Hilbert space H, then there exists a unique bounded operator A such that phi of xy is equal to x with ay. So this is sort of an analog of the Ritz representation theorem, right? So the Ritz representation theorem last time was what? Like if you have a linear functional f of x, then you can write it as, you know, x with x naught. So this is the next level up of the Ritz representation theorem. And if you look at the proof he has of theorem 4.33, it starts with the Ritz representation theorem and kind of works from there. So next up, he defines something called a coercive functional, which I don't ever remember hearing this language before, but you know, I've lived a somewhat sheltered life, so coercive functional. And you have a bilinear functional phi on a norm space E. So let's say phi from E cross E to C, where NLSE, I think, is coercive or elliptical if there exists a positive constant such that phi of xx is greater than or equal to k times the norm of x squared for all x in E. And this definition is interesting primarily because of, I mean, he gives an example of such a thing, example 15. And that might have relevance to like a particular kind of differential equations, but I'm going to get to the theorem here. Focus. So the theorem that is based on this definition, this is the Lax-Milgram theorem. It says, let phi be a bounded coercive bilinear functional on Hilbert space H for every bounded linear functional f on H, there exists a unique xf in H such that f of x is equal to phi of x comma xf. So this is, again, reminiscent of the Ritz representation theorem. Now the proof of the theorem, the last proof I skipped wasn't much. I mean, it's about a page, but actually the steps in that theorem are pretty straightforward, I think. The steps in the proof of the Max-Milgram theorem are also pretty straightforward for a part, but then it gets a little bit, it's got a proof by contradiction at the end of it. It's a little bit sneaky, But I thought we should at least put it on the board and look at it. So, is this true? I think this becomes the Ritz representation theorem. This is the Ritz representation theorem when you take the case that this is the inner product. So what this is in some sense saying is that if you've got a bounded coercive bilinear functional in a Hilbert space H, it behaves like an inner product, at least with regard to the Ritz representation theorem. See, because this is just, it's just think of x naught being your xf, and and I do think that there were terms and conditions I keep forgetting to mention, but this is I think that's for a bounded linear functional. And because because if it's not bounded, well, if you took an unbounded linear functional and assumed such a vector existed, I think that would imply that the linear functional was bounded, and then you'd be in trouble. If it's unbounded and then you can prove it's bounded, well, then that's problematic, right? Yeah. Let's see here. Let me see where I am. So the next section we've got is on the adjoint. So let me tell you where we're going here. Let's see here. Well, yeah, let me go ahead and cover this section. It won't take us long. So here is section 4.4, which is on adjoint operators. And so here's the definition. Let A be bounded operator on Hilbert space. All right. H. Then A star, upper star, from H to H, defined by the inner product of AX, Y equals the inner product of X with A adjoint Y for all X and Y and H is called the adjoint operator of A. Right. He's